All right, we're going to solve this differential equation in two different ways. This is going to be great fun. Let's jump right in. The first thing we're going to do is we're going to solve this thing by separation. Right, because you may notice that this is separable. You've done separation before. The second way we're going to solve this problem is actually via a much more general purpose technique. It takes a little bit more work at times. But that technique is called undetermined coefficients. So let's go through separation just so that we're all on the same page here. So I'm first going to say, well, okay, remember for separation, I need to be able to write my function, the right-hand side of my differential equation, that is, as a product of a function of y and a function of t. Well, okay, so if we do this, in this particular case, I can say dy dt is, and I'm going to factor out my negative 0.2, and that leaves me with y minus 15. And I can think of this as my function of y, and I can think of this as my function of t. And now I can go straight forward, sorry for the handwriting here, I can go straight forward on this and just do separation. So I've got dy over y minus 15 equals negative 0.2 dt. Integrate both sides. So natural log of y minus 15 is equal to negative 0.2 t plus a constant. Exponentiating both sides. You've done this before, so I'm going rather quickly through this piece. And then adding the 15 over, no problem. So by separation of variables, this is actually relatively straightforward. Right, so we kind of know what our solution is going to look like. And if we had an initial piece of information, we could go get that c. So let's actually do it. Let's say we had like y of 0, for example, is equal to 3. Doesn't matter what it is, just as an example here. So if we put in 0 for t, I'm going to get 3 out for y. So 3 equals c times 1, because e to the 0 is 1, plus 15, which implies that c is negative 12. Right, so we get our solution, which is negative 12 e to the negative 0.2t plus 15. So with my initial condition, I actually have a nice solution. Okay, let's now do this problem in a slightly different way. Right, this new method is what's called undetermined coefficients. Coefficients. Oh boy, if I could spell that correct. That's a C, just go with it. That's an N, just go with it. We're using a kind of a bad stylus, so I'm sorry. So here's the deal. So we have the differential equation, dy dt equals negative 0.2y plus 3. And I'm going to see this as a homogeneous piece. All right, this little guy that I'm highlighting in blue here, that's the homogeneous part. Right, and then I have the non-homogeneous part sitting over here. And homogeneous versus non-homogeneous is, am I adding anything onto the y or am I not? Right, so the homogeneous part, I can look at this differential equation as really the sum of two pieces. I'm going to solve dy dt equals negative 0.2y. That's, again, just the homogeneous differential equation. And this being such an easy differential equation, I can just write down the solution to it. You can get here several different ways. Separation of variables is one way. I'm also going to guess a solution that has the exact same functional form as the non-homogeneous part. So I'm going to guess that my solution let's put a little, I'm going to call that homogeneous. My particular solution is what we call it, is the exact same type of function as the non-homogeneous part. So that type of function is constant, so I'm just going to call this thing constant. And then my analytic solution is the sum of my homogeneous solution plus my particular solution. All right, so in this particular case, right, I have C naught e to the minus 0.2t plus C1. Right, now, you're going to notice that this is exactly the same form as the solution that we found from separation of variables, but we got here in a slightly different way. This thing was the solution to the homogeneous part, and this guy was our guess on the non-homogeneous part. And I guess that because it's the exact same functional form. Now, the reason that this is called undetermined coefficients is because there are now quite literally two coefficients that are yet undetermined. So we have the differential equation, y prime equals negative 0.2y plus 3. And we have the initial information, so y of 0 is equal to, I think I used 3 before. We're going to use those two pieces of information to determine the undetermined coefficients. So let's do it. If I use the initial piece of information, y of 0 is equal to 3, that tells me that that 3 equals C naught plus C1, plugging in 0 for all the t's. And if I use the differential equation, well, let's see, the differential equation is kind of interesting. If I take the homogeneous part of the differential equation and put the homogeneous part in to here and to here, I will automatically be satisfied, except for that plus 3. So really the only interesting part here is the particular solution. So I'm going to put the particular solution, I'm going to put y particular into the differential equation that says ODE, just go with it, and see what comes out. My particular solution, my y particular, is, oh my goodness. My y particular is just C1, and if I put that in, the derivative of C1 is 0, equals negative 0.2 times C1 plus 3. Do a little bit of algebra here, so negative 3 equals negative 0.2 C1. And so C1 is equal to, well, let's see here, negative 3 over negative 0.2, which is 15. Well, gee, what that tells me is that my solution is, so C1 is equal to 15. From this piece up here, that tells me that C naught is equal to negative 12. It's got to be. And so my solution is y equals negative 12 e to the negative 0.2t plus 15, which is precisely the exact same place that we were before. So let's talk through the steps one more time for undetermined coefficients. I look at my differential equation. So here's my guy. My differential equation is a linear differential equation, and I break it into a homogeneous part and a non-homogeneous part. I solve the homogeneous part, so one might call that, say, step 1. Solve the homogeneous part. In step 2, I would say let's guess a solution for the non-homogeneous part, and this has the same functional form as the homogeneous part. So since I was a constant function up here, I used a constant function down there. If this was linear, that would be linear. If that was cubic, that was cubic. If that's quadratic, that's quadratic, and so on and so forth. Okay? Then what I did was said, okay, my solution is going to be a sum of the homogeneous and the non-homogeneous part because it's a linear differential equation. So I wrote that down, and now the rest is detective work. I have two pieces of information that I can use, the differential equation and the initial condition. And if I use those, I can get relationships between the coefficients. So I use the initial condition to get one relationship, and I use the differential equation to get another. Oops. Put all the pieces together, and I have my solution. Now, this seems a bit more cumbersome than separation of variables, and admittedly that it is. We're going to see that it's actually pretty useful in subsequent videos.